Okay, so let's move on to section 6.1, the general issues. And I put 4 general issues here for the application layer. First of all is how ports work, the port number, and how server works, and the classification of servers. We will see that we classify server into connection-oriented, connectionless, concurrent, and iterative. So we would have 4 combinations for servers, 4 combinations, either concurrent or iterative, either connection-oriented or connectionless. And then finally, we talk about the characteristic of application layer protocol messages. So we will see that everything on the application layer are binary. They are coded in binary. But everything on application layer are mostly coded in ASCII. And we need to know why. Why the application layer message are coded in ASCII instead of binary. Okay, we know the port number is the TCP or UDP port number. In the TCP or UDP header, there's a source port number, destination port number, and it's a 16-bit port number. So the number could be up to from 0 up to 65, 535. Okay, and the lower number are well-known port, reserved for well-known port. So the number. So there are some reserved ports for well-known services. Okay, for Telnet, for SMTP or POP3 or MF4, or for FTP, or for www. There are some well-known ports reserved that those are server ports. The server needs to be well-known. And there are some ports which are also server ports, but could be registered. Those are non-well-known server ports. So there are some registered ports. Usually you don't need that much. So server port, but not well-known, but need to register. And what are these? Usually these are some remote procedural call server, RPC servers. And they need to register themselves so that the client would know where they are. And then you need to register the port number to the registration server so that the client would ask the registration server to know where the RPC server are. But there are at a high address, high port number, there's a space for client. The client does not need to be well known. They need to be well known. They don't need to register. They don't need to register the port number they use. So they would use this so-called dynamic or private port number, and usually it's picked by the kernel, decided by the kernel for the client. So on this figure, you will see on this machine, there are 4 servers running as daemon processes. Okay, so you have 4 daemons, and each of them bind themselves onto a particular server port number, onto a particular well-known port. So, so we have seen in chapter 5 that you could call bind. The bind system code would allow a socket to bind itself to a particular port number, so that you are telling the server, you are telling the kernel of this machine. So the daemon will tell the server of this machine what port number I'm going to bind myself to. So if there's a segment, if there's a packet or segment coming in destined to this port number, then the segment is mine. You would deliver the segment to me. So this well-known port can only be used for particular services, and the server here needs to bind themselves to this port number. And because they are well known, so the client will know where the servers are by their IP address and port number, and these are the port number they need to know. And for the client, the client would also have IP address and port number, but the port number is dynamic. It doesn't really matter what number it is, and usually these numbers are picked by the kernel. The kernel decides the number, pick a number for this particular client. Okay, so in this scenario, you have 2 clients, one on each client machine, connecting to 2 servers. And on this server machine, there are 4 daemon processes running and waiting on some particular well-known port. So that's basically how ports work. And you might ask, can I have 2 processes listening on the same port? Can I? Or can I have 1 process listening on 2 ports? Let me say it again. Can I have 1 port with 2 processes listening on? The answer is yes. And can I have 1 process listening on 2 ports? The answer is yes. So I can have, so it's possible that you will see the server here in the later sections, that the server, many of the servers that achieve concurrency, meaning that they can handle multiple clients at the same time. They can achieve concurrency by forking child processes. So if this process fork child processes, their child process would also listen on the same port number. So for this one, I fork a child process. Then the child process also listen on port number 21. So and then so then I would have if I have 10 child processes, and 1 parent process, so I would have 11 processes, all listening on port number 21. And for those 10 child processes, they would each handle a client. So suppose I have 10 clients, then I would have 10 child processes talking to them. And I'm a parent process. I also listen on the same port number, 21. And what I'm doing, I am listening for new client. I'm waiting for new client on port number 21. But my 10 child processes, they are serving the 10 clients. Okay, so that's one possible scenario. So we could have multiple processes listening on the same socket, listening on the same port number. Okay, how about having a process listening on multiple port number? Can I? Yes. Um, that's the next issue here. The next issue is how servers start. How servers start. Okay, we can run a server as a standalone server. Just like the previous page, we have 4 server processes running on the machine, and each of them is a standalone process. We could also have a super server, super daemon, running as a watchdog for me. Okay, so I can run my server process dedicated for that and a port number to serve the client. So then so that's called standalone. It happens when suppose I have several server port number to offer services, but on the average, there are not many clients connecting to these servers. So I'm not running a website, commercial website. I'm just running a company website or my personal website. So there are not many requests every day. So it doesn't bother. You don't need to run the server all the time. You could have a watchdog server. A watchdog server watch the port for you. And once there is a request coming in, if there's a client coming in, then you run the server program. So at the time that there is a request coming in, you run the server program. But usually you don't run the server program. So then I would have a inetd, which is a super daemon. We call it super daemon. And the reason why we call it super daemon is because most network server processes are forked by inetd. So it's the parent of many server programs. It's a server of many servers. So that's called super daemon. And we could have this super daemon to listen on these port numbers, for us. So in that case, then we would have, say, instead of having 4 processes here, running standalone, we could have one inetd and creating 4 sockets. The inetd is a process that could and it create 4 sockets, and it binds the 4 sockets onto this port number, and then it does I/O multiplexing. There's a mechanism called I/O multiplexing. It would then call select. Select is an I/O multiplexing system call that would block on this socket. So if there is no request, no client coming in, then it will continue to block there. But if there is a request coming in, then the select system call will return. That means the blocking condition has been removed. Okay. Then the inetd will then call the specific server program to serve the client. Okay, so I talk about the I/O multiplexing, which is a term used in circuit programming, and we wouldn't talk further on that, but I/O multiplexing in circuit programming is a very important skill or concept in network programming. If you take the course of network programming, how many of you are taking or have taken network programming, which covers circuit programming? How many of you? None. Okay. there's a course offered by Professor Wu, right? Wu Yicheng. It's on circuit programming. Okay, so either you have standalone or a watchdog program, which is inetd. Okay, for standalone, you would need to explicitly start the program if there's a configuration change to take effect. So usually the every server. So this is a concept that you need to know about managing a server or configuring a server. Usually, if you run a server, and how the server should run should not be hard-coded into the program. You don't hard-code the configuration of the server into the program. And you don't put it into the parameter of the program. No. You put it into a configuration file. Configuration file. So usually when you manage a server program, you need to modify the configuration file. So for example, if you need to be a server administrator for email server or for web server or FTP server, you need to study the configuration files, the format of the configuration file, because those are there are many configuration parameters that you need to set. And here I'm talking about if you run it as a standalone program, and if you need to change the behavior of the server program, then you need to change the configuration file. But when you change the configuration file, it's not read by the server. You need to restart the server, because when you restart a server, it reads the configuration file. So the server only reads the configuration file when it is initiated, when it is started. Okay, so that's one problem with the standalone server. And crashed standalone server might not be noticed. So for example, if your web server is down, you wouldn't know that until somebody tell you, okay, I couldn't access your server. Okay, so that's another problem. However, it provides better performance because it's already there. It's always there. The server program is running there all the time. Should be there all the time. So another one is a watchdog program, which is inetd. And since it is a watchdog listening on multiple ports, and if there's a client coming in, it would execute a specific server program. And when it executes a specific server program, the server program will read the configuration file. So remember we said that a server only reads its configuration file when it is started. When it is started. Okay. And a fresh copy of the program, the server program, fresh copy of the server program will be spawned or forked on demand. But the disadvantage of this is that latency. It takes a while for the watchdog program, for the inetd to bring up the server. It will need to call the server, execute the server. So it takes a while for the server to get ready. So right now, most of the system, if they run server, they would use a standalone. And the reason why there were times that we use inetd to be a watchdog is because when the machine is small, the memory size is small, you don't want the server program to occupy the memory. If you have a server program occupy the memory but does not serve the client often, then it wastes a memory resource, right? But now, because the memory size is large, usually gigabyte, in gigabyte, it was counted in megabyte, but now it's counted in gigabyte memory. So since the memory size is big, so it doesn't bother much to have the server standalone running there all the time, even though they are not serving any client. Okay, so most of the time we are using standalone. And about crashed server, if it's crashed, so instead we need to have a mechanism to check the server availability all the time. So there are some system control tool that would help you to do that, to check your servers. Okay, that's the second issue. So we do see some process listening at multiple ports. We also see some ports being watched, being listened on multiple processes. And the servers. So here we are talking about concurrent issue. Concurrent versus iterative, and connection-oriented versus connectionless. we have got familiar with the connection-oriented and connectionless. Connection-oriented means that you need to set up the connection first before you can send request. Connectionless means that you don't need to establish a connection first. You can send the request directly. And so by connection-oriented, it means that you need to write on top of what? On top of what transport protocol? On top of TCP. So connection-oriented means TCP, while connectionless means UDP. So that is easy, and we have clarified that in chapter 5. Now we need to know the difference between concurrent and iterative. And if the service time of two clients could overlap, then we call the service model concurrent. If the service times of two clients cannot overlap, then we call it iterative. So let me give you an example. If you go to a fast food restaurant, did you ever have the experience of you order something and the server take your order and then give you the food you need, and then you pay and then you leave? Okay, but there are also some situations that you order fries or a hamburger. Now you need to wait for 2 minutes to cook. So what you would do? Would you stand there for 2 minutes while the server get idle? The server get idle and you wait. No, the server will ask you to stand aside, right, waiting there, so that he or she could serve the next customer, right? Okay, so the customer, while you are waiting for your hamburger to be cooked, the next customer will place the order, will start the service time. So in a sense that your service time is overlapped with the next customer, right? Then we call this server as concurrent server, because they can serve you and also serve the next customer at the same time. Okay, actually the server is serving you and also serving him at the same time, even though the service time of both customers overlapped. then we call it concurrent. But in the previous model where you wait for 2 minutes and the server does not serve the next customer, then we call it iterative. It means that the server cannot serve the next client before the current client ends its service time. Before the current customer, the current client ends its service time, the server cannot serve the next client. Then we call it iterative. Okay, then the question now is, should we run in iterative mode or in the concurrent mode? Okay, if that depends on what? The length of the service time. If the service time is short, then what? We could run on either mode, right? But if the service time is long, then we need to do what? Concurrent, right? If the service time is long, it means that if your service time is long and you still run iterative mode, it means that some customer will be angry, right? They will need to wait for a long time. So my service time is 5 minutes, and before you finish my service time, you couldn't serve the next. Even though I'm waiting, I'm just waiting, you still cannot serve the next customer. So it's bad to run iterative in this case when the service time is long. So the problem now is, if the client request can be served quickly, then it's okay to run iterative mode, right? And what kind of service what kind of request will have short service time? Well, just a simple, usually a simple query. For example, DNS. DNS could be short. I just want to ask you the IP address, the domain name from domain name to IP address, or the SNMP, simple network management protocol. I just want to ask you a value of a management object. Okay, I just want, or P2P query. I just want to ask whether you have this file. So the service time is short. Then we could run iterative mode. But if the service time could be long, like for example, the files transfer will have long service time, and I want to get a web page. If the web page is not short, not small, then the service time will be long too. So for those requests, they would need a longer service time. Then you need to run iteratively, concurrently. Then so we have differentiate concurrent and iterative. Then the next question will be, is it natural to combine iterative service mode with connectionless server, or it could combine with connection-oriented server? Is it natural to run concurrent mode with connection-oriented server? Connection-oriented. Is it natural? Yes, it's natural, but it's not necessary. So the conclusion is, it's natural, but not necessary, not definitely, not always. So you will see that among these four combinations, these two are most common. So you would have concurrent connection-oriented server, concurrent TCP server, or iterative UDP server. That's more common. but you will have less iterative TCP server or concurrent UDP server. You will have less of those combinations. But sometimes you do have, but less often. Let me give you some possibility that you would have the less often combination. For example, you have you run voice over IP server or voice over IP gateway, and it's on UDP, right? You run on UDP, so it's connectionless. But the service time is long because the phone call could last for 5 minutes. So the service time is long. So you need to run concurrent but connectionless server. So it's possible that you run concurrent connectionless server. Okay, how about iterative connection-oriented server? It's less. It's even less than the first combination. You have a TCP server, but run in iterative mode. It's less often. It's less often because if it's going to be short, the service time going to be short, but it needs to be reliable. Short but reliable. You could do that, but most application, when the service time, if they have short service time but need to be reliable, they would put the error control in the application layer themselves. They would, for example, remote procedural call is one example. Remote procedural call run on UDP, and the service time is short, just a procedural call. But it needs to be reliable. So instead of expecting instead of expecting the transport layer to run on TCP to provide a reliability, it does the reliability by itself in the remote procedural call. They would check the reliability. So instead, I would use a UDP, but I do my own reliability control. I do my own error control. So that's why it's much less often to have iterative connection-oriented server. But there are some concurrent UDP server, like voice over IP. But the middle two, the second and third combination are the most often, where the first one will be, say, most email server, file server, web server, they all run the second mode, the concurrent connection-oriented. How about the third one? What run on iterative connectionless? Those SNMP, DNS. Actually, DNS run on two ports. They run on UDP port and also run on TCP port. So I'm providing service on two ports, UDP and TCP port. So if you are asking, if you can either send me your request, send me your DNS query onto the TCP port or onto the UDP port, which are all fine because I bind myself to this two port number. So there are servers, the DNS server, they bind itself to two ports. And these two ports are not just two numbers, but they have the same number. What is the name? What is the ID of the number for the DNS port? 20 something. Okay, but they are on two different on TCP and UDP ports. So I can provide services on both TCP and UDP ports. for DNS. On XNMP, it provides service on UDP port, but and also provide iterative service because the service time is short. And many P2P application, many P2P, in P2P there is no server, but everyone is peer. So everyone is a peer. So every peer needs to listen on one UDP port and one UDP port and also one TCP port. So I'm using my UDP port to send queries or to receive queries. But I've used my TCP port to do file transfer, to do data transfer. So it use both. But on the UDP port, I run what? Iterative mode, right? I run iterative mode. Okay, so we have seen these combinations. Understand why we have these four combinations. And do they run on? So here's a list of popular application. These popular application, they run on these. They run with these application layer protocols, and as you can see, the voice over IP, many of them are proprietary. Streaming is proprietary. P2P are proprietary. But we can tell that what protocol they run, what transport protocol they run on top. Here they run TCP, but here they run mostly UDP. And DNS run both TCP and UDP. So you can, it provides service on both TCP port and UDP port. Okay, so since we have mentioned that there are two popular combinations of the server mode, which are iterative connection list and concurrent connection oriented. So let's look at these two figures. And we have seen the similar figure in chapter 5 last week. But here we take a look at it again, and there's a subtle difference in this figure. In chapter 5, the figure we shown in chapter 5 last week, the figure is iterative mode. They can only run iterative mode, but this figure it run concurrent mode. So let's explain this first. Okay, so again, the server needs to call the socket, and the client needs to call the socket system call to get a file descriptor. And remember, accessing a socket is the same as accessing a file in Unix or Linux. Okay, so you got a file descriptor first, and a kernel establish a structure, a set of structures for you. And then you call the bind system call. The bind system call is you want to tell the kernel that you want to bind yourself to a particular port number. Usually a well-known port number. You want to bind yourself to a particular well-known port number, and you are telling this to the kernel. And then you call listen system call. It tells the kernel that I'm going to listen on this port number, and please prepare connection queues. There will be two connection queues. One is incomplete connection queue, and one is complete connection queue. Prepare for TCP three-way handshake. So it informs the kernel to prepare connection queues for three-way handshake. And then it enters into a loop, an infinite loop. And the first function to call in the infinite loop is called accept. So here I'm telling the kernel, the system call accept is telling the kernel, okay, get me something. Get me some client request. Sorry, get me some client. Get me some client. Give me a client. Okay, but if there's no client coming in, then the accept system call will block. It will block, and the process will sleep. The server process will sleep. But if there's a client coming in, then it finished the three-way handshake, and then the accept system call will return. It will return, and the process will be awakened, and the accept system call will return. And when it returns, it call the next function, which is fork. It will fork a child process. And it would let the child process execute this while itself, as a parent process, while itself execute this. So it will close the file descriptor of the child process and then come here. So it would wait here indefinitely. So if I'm a parent process, I would just listen and fork, and then I keep waiting for new client. So I'm just waiting for a new client. But if there's a client coming in, I fork a child process and let the child process serve the client. It's like your advisor, right? It does not do the project. It initiates the project. You find the money, find the project, and then ask the assign a student to execute the project. No, I'm not. I'm not doing that. I also do the project. Okay. Okay, so the parent just do this, waiting for new client. Once there's a new client, it fork a child process. And the child process will then interact with the client. It would call the read and write. Read to read the request. Write to prepare the response, and then write the response back to the client. And the client here would do the write and read. Write the request and then read the response. Okay. And here it close. The child process closed the listening socket while the parent process closed the client. I mean the client socket. Okay. And once the client finished the job, it would terminate itself. So the client process will terminate, will close and terminate itself. Okay, so so consider if you do this, if there are 10 clients connecting to this server, then there will be at the server there will be 10 child processes and 1 parent process. Okay. So you achieve concurrency by forking child processes. So the concurrency is natural, and the service times of these child processes are overlapped together, so they could overlap with no problem. And we would see this is a basic way to achieve concurrency. And there are many variations to achieve concurrency. For example, you can change the process to thread. Instead of forking a child process, you create a thread. And creating a thread is cheaper than forking a child process. If you know the difference between thread and process, it's covered in operating system. It's a thread is sometimes called lightweight process. And within the process, you could have multiple threads. And the thread, if say I have 5 threads within this process. Then these 5 threads, they share the same program code, but they don't share the program counter. They share the program, they share the data structure, but they don't share the program counter. The only thing they don't share is a program counter. So you could have multiple threads running on the same body. So it's like it's like 5 souls running on a body. So if you think process is a body with the program, with data structure, with stack, then and registers, okay, then the thread does not have body, does not have the program, the data structure, but it has the soul. The soul is the program counter, the register, the stack. Okay, those are the soul, but the body, it does not have the body. So, so forking a child process would need to create a memory space that has a program, that have data structures, and that have stack, and registers. But creating a thread does not. You don't need to create the body. You just need to create the soul, which is the stack and the registers. So it's much cheaper, much easier, much faster, and consume less memory and CPU time. Okay, so thread is lightweight compared to process. And what else? You could, if you have a server, a server machine that needs to support 1,000 clients, then definitely you don't want to fork 1,000 processes, because usually I don't know on the modern computer, on the modern server PC, whether you can limit the number of processes you could create, but it was hundreds. It was only hundreds, like 500, 600 will be the maximum number of processes you can create on a PC. But probably now it could be higher, but I don't know how high it could be now. But over thousands of processes will be incredible on a server machine. So in that case, then you could change to thread. But even with thousands of threads, it will be quite amazing, right? So there are other variations to improve that. In Apache server, they have provided the Apache server, which is the well-known, the most popular web server. It provides 2 versions. One is a process version and one is thread version. They would fork child process or create threads. But because forking child process would take time. Creating thread would take less time, but still take time. So they have a mechanism to speed up. They call it pre-fork or pre-thread. So they can pre-fork a pool of processes. I can set aside, say, 20 processes, idle processes that have been created already. So if there's a new client coming in, then I would just dispatch an idle process to serve the client. I don't need to fork at that time. I don't need to fork on demand. I have pre-fork, okay? And so if there's a burst of client coming in, then I could serve the burst of client easily, as long as the burst is not too long, over 20 clients, then I could serve immediately. And when I finish dispatching the client, dispatching the child processes, the pre-fork child process to serve the client, then I have time left as a parent, then I check the pool. I check the pool of idle processes and find that there are, say, less than 5 idle processes in the pool. Then I create more. I fork more idle child processes, so that I can maintain the idle process in the pool to be between 2 bound, upper bound and lower bound. Say lower bound between 5, upper bound 20. So I can keep the idle processes there, and that will speed up my service, my initial it will shorten my initial latency. Same for the threaded version. I can have some pre-threaded threads, so that I can I don't need to create a thread on demand. That's in Apache server. And what if I there's another philosophy we will see that in Darwin server. In Darwin server, you will see that they don't bind a process to a client. The concept is not bind a process to a client. No. A client will be in Darwin, which is a streaming server. A client will be served within its service time. It will be served by multiple processes or multiple threads. Actually, it's implemented in thread. So a client will be, first of all, when a client comes in, it needs to do setup. So there's a thread who does setup for the client. So then it will serve the client. And then the client will then enter into the next stage, say start streaming. Then there will be another thread which would pump the video audio traffic to the client. And when the client finishes, it's about to when the client, if the client send some remote control, say fast forward or slow motion, and then that request will be served by another thread. Okay, so over the lifetime, over the service time of the client, it will be served by, say, 3 or 4 threads. And we call it, the model is called worker thread, the worker thread model. And in that model, we don't bind the thread, a thread to a particular client. In fact, no binding, no such binding. A client will be served by multiple threads over its service time. So, so then it will become more scalable because you don't need to have so many threads. So suppose this server is serving 1,000 clients simultaneously. I don't need to create 1,000 threads. I probably have just 4 types of thread, and each type could be just 200. Well, sorry, each type could be just 10 threads. So I have 10 threads for initialization. I have 10 threads for playback, retrieval. I probably have 10 threads for remote control. I have 10 threads for clean up. So I only have probably 40 threads totally to serve 1,000 clients. Okay, and that's the worker thread model that you will see in Darwin. Another service model you will see, not here, but in the Squid server. Squid is an open source server program for proxy. As a proxy, and as a proxy, you work as a gateway in a network, and there could be over 1,000 client or connection passing by. Suppose there are 10,000 flows passing you simultaneously. then instead of for this proxy, instead of having a thread or a process to serve each flow or each connection, you would have just one process to serve everything. And what would you do? You would have one process, but 10,000 sockets. Actually, 20,000 sockets, because as a proxy, you need to have one socket for each, for the client, and one socket for the server. So if this is client and server, then as a proxy in the middle, you would need to intercept the TCP connection. Then you would have a socket for this client and another socket for this client. So if there are 10,000 flow, 10,000 TCP connections passing by, then you would have 20,000 sockets to handle, to listen to. So I would create 20,000 sockets, meaning 20,000 file descriptor, and I listen. I do I/O multiplexing by calling select. There's a system call called select, which allow you to do I/O multiplexing on these 20,000 sockets. But I'm just one process, and if any of these socket is ready, have something to handle, then I handle them. I'll be wake up and I handle them. So I'll be busy handling this socket request. Okay, if there are requests or response, then I would handle them. And I just have one process, but I need to be concurrent. And doing I/O multiplexing will allow me to be concurrent to serve these connections at the same time. So I'm not a client, I'm not a server, but I'm a proxy in the middle of client and server. And I could have just one process, but still be concurrent, serving the client and server. So that's to the extreme. So if you say squid is one extreme, it's the extreme. It's very extreme that you have just one process, but still concurrent and connection oriented. But you will see in the middle, you would have some model like Darwin, which is worker thread model. And you will see like Apache server, it has pre-fork or pre-thread. And you will see some primitive model like this. You fork on demand. And you will see some model that is strictly iterative, no concurrency. And for this discussion, I think this is an interesting discussion, and it's there's a sidebar in this chapter, but it's the very end of this chapter. On page 540, common pitfalls, alternatives to server concurrency. On page 540, alternative to server concurrency. There are two paragraphs on this, which are things I just described. So I'm in this chapter we have covered 8 applications, and each of the applications come with an open source implementation, open source server program, and I summarized their model. I mean their model to achieve concurrency, which are things I just described. Okay, if you roll back to see this, then it's a very primitive model without concurrency. It's iterative. So the server would, and this is the same as the one in chapter 5. This figure is the same as the one in chapter 5. But this figure is not the same. It's not the same as the one in chapter 5. The one in chapter 5 does not have concurrency. It does not fork child process, but here it does. And it does this to provide concurrency. Okay, but here, the service time cannot overlap. When I'm engaged, okay, I serve this, and then I roll back to take the next request. So before I finish the response, send back the response, I cannot take the more request. Okay. It is okay. Okay, the final issue is on the, I need to finish this. The characteristic of application protocol messages. And you will see that the application protocol messages are variable length. Variable in terms of message format and length. The message format and length are variable with the why. Why it's a variable? Why it's not fixed? In TCP, in IP, in Ethernet, wireless LAN, we all have fixed length header, right? And the fixed fields. But here it's not fixed. Why? Because there are too many. There are too many, and there are too many parameters, first of all, and each parameter value, the value of for those parameters are variable length. The values are variable length. For example, URL, the length of URL couldn't be fixed, right? The length of domain name couldn't be fixed. The length of some parameter value couldn't be fixed, like a string. If it's a string, it couldn't be fixed. It's variable length. So, so why it's variable format and length? It's because the parameter values of this application protocol are variable length. They couldn't be fixed. You can't force them to be fixed. Okay. Secondly, the data type are variable. Okay. For example, in the mail or in the web page, there could be many different objects embedded. And if it's text, then it could be in different languages. So the data type are variable. And for text or non-text data, they are not. The data type could be variable. And thirdly, some of the protocols are stateful. Stateful here means that the server needs to remember something. The server needs to remember something about the client. For example, if you use a FTP, you know that FTP server remember the client's working directory, right? The server does remember the client's working directory. And if you want to change to another directory in the server, then you need to change directory. You need to issue a command to change the directory. So the server remember you and remember something about you. But not all servers are stateful. There are some servers which are stateless. For example, HTTP server are stateless. A pure HTTP server is stateless, and it does not remember you, and it does not remember something about you. But you would say that, okay, I go to shopping for one hour on that website, and it remembers something about me, and it remember what I purchased. That's that statefulness is added on by something called cookie. We will explain that how to turn stateless web server into stateful by cookie mechanisms. But the original HTTP protocol is stateless. Okay, it does not remember you. It's just one request, one response, and it does not remember what you have asked and who you are. No. So some server have maintained statefulness, but some don't. But they all have this. And as a result of this characteristic, the application protocol messages are usually in ASCII, not in binary, because it's variable length, variable format. So it's better to put it into ASCII directly without binary coding. So it's plain text usually. Another reason why it's ASCII plain text is because it's easier for human to understand. So it's easy for human to understand. So you don't have to transform into binary again. You don't need to do coding into binary again. So it's usually in ASCII. But another bigger reason is the bigger reason is that it's variable length, variable format. So we would just put it into binary. So that's one unique thing about application protocol messages, which is quite different from the protocol header we have seen in the other lower layers. Okay, we will stop here. For the next class will be Thursday, as usual, and no class next week.